right, so since we're running late and some of us are bus lagged, I'm just going to ask John to give me the hook sign when he wants me to stop, and I'll wind it up within 45 seconds, give or take. So I could talk about a lot of things relating to parsing. I kind of had this grand ambition that I was going to like lay out this formal meta theory for like how you can, conceptualize parsing as a general sort of philosophical thing, and we could go from there. And I decided that was like really, really, really ambitious, partially because it's like sort of hard to talk about some of these things, especially like it's hard to put it on slides, it's hard to gesture about it, it's hard to say the words. But there is a lot of depth here, and there's a lot of generalization that's under all of the specific examples that I'm going to show you today. And as you study it further, the generalizations kind of begin to appear to you more. So what we're going to do, just a quick show of hands. How many people here have implemented a parser? And I don't mean like regular expressions, I mean like a parser. That is a surprising number of you. I hope a meteor doesn't hit this building. That's like half the people in the world who've ever implemented a parser are in this room. This is not a very common thing to do. It's definitely one of the more interesting tasks. But the fun thing about parsing is that it's really easy to get something simple going. It's just that you find yourself running into trouble once you start to go further than that. So before we get into that, I want to show something really quickly. Is that legible?
Yes.
Yes. Are we good? Okay? All right, that's good. All right, I want to be clear about the formalism that we're going to be using to talk about grammars, because parsing is fundamentally the problem of consuming a linear sequence of tokens in accordance with a context-free grammar. And there are several ways of representing context-free grammars, but eBNF or BNF is the primary one. And you would basically say something like this, right? So this is your double colon equals operator thing. So if I wanted to represent a grammar for like, addition operations, maybe addition and subtraction, I would say something like, I can have an expression followed by a plus followed by an expression, or an expression followed by like apparently an underscore because I can't type, followed by an expression, or like maybe, some sort of numeric thing, right? This is basically BNF. Nothing too particularly fancy about this. And you can extend this quite heavily. There's a lot of formal, like really beautiful formal math behind this stuff. Basically, this formalism, you can think of it in a little bit like a recursive regular expression, and it describes a class of languages known as the context-free languages. So in the pantheon of languages, you have like regular expressions are here, and they describe the regular languages, and then context-free languages are above that, and they, everything that's a regular language could also be context-free. Like you could embed regular expressions in this, that'd be fine. And then above that is context-sensitive languages, which is things that we don't generally deal with, but like Haskell and Python have to deal with this problem, right? Where their grammars are actually context sensitive. And then on top of context sensitive languages, you have recursively enumerable, and then, something like that. Like recursive stuff comes above that, and we stop caring because it becomes really, really intractable. We generally, like sitting in the context-free zone is really, really good, because you're starting to get to the point where certain questions are undecidable. Like for example, it is impossible to take an arbitrary grammar and mechanically look at it and decide whether or not it can be, is unambiguous across all input. That is actually equivalent to solving the halting problem. So even something as simple as like a recursive regular expression, like it's a very complex, it's a very deep formalism. But so some problems are starting to become undecidable, but like most problems are still very decidable, right? You can compose context-free grammars together. Like things like that are very tractable. There's a lot of analysis that we can perform on context-free grammars. Not quite as much as with regular expressions, but still quite a lot. So generally speaking, as you move up this pantheon of like languages, formally speaking, fewer and fewer and fewer questions can be answered. So it kind of sucks, right? Like context-free languages, for example, like a parser will always halt, like on any finite input. It's guaranteed to always halt. You can't get into infinite loops. A Turing machine is not guaranteed to always halt on finite input. So yeah, don't use Turing machines. Anyway, this is kind of the formalism that we're going to be working in, and our task, as sort of, if we think about the algorithmic side of this, is to design algorithms which can mechanically translate this formalism into something that can run preferably on real hardware, with real memory constraints, on real inputs, in reasonably real time. That's kind of like the whole goal of like parser studies, like parsing theory as a field, is to translate this into stuff like this. And we'll get to that in a second. So there's a lot of different techniques for this that people have devised over the years. And those of us who've written parsers, like basically all of us started by implementing something called recursive descent. So recursive descent is great, because if you know how to write a recursive function, you can write recursive descent. It's really, really, really straightforward. So we're going to write a recursive descent parser for this grammar up here. So the grammar is in the comment, right up at the top. It's a simple expression language. It's a little different than the one that I showed, kind of the formal one on the previous slide, but it's still a context-free grammar. And what we're saying is an expression can consist of a terminal, or sorry, a token, a term, followed by times, followed by another expression. It consists of a term followed by dividing, followed by another expression, or it can consist of just a term. And terms can consist of parentheses wrapping around an expression, or it can just consist of the number 1, because I didn't want to implement regular expressions in the back of the room. So we have a somewhat simplistic thing here. All right. These examples are going to be in Scala. If you're not comfortable reading in Scala, hopefully this will still be intuitive. It won't be until the end of the talk that I start to like use more advanced Scala features, but like hopefully this is clear to anyone who understands functional programming. Also, I didn't bother compiling these examples, so they might not work.
A little bit, I don't know too much about parsers, but what makes it context-free?
Context-free, great question. So the best question, like why it's context-free versus context-sensitive, is in a context-free language, you cannot take the result of a previous parse, like a previous part of your parse, and use it to compute the rules that you're going to follow next.
I see.
So a great example of this is Python, right? So Python, the class body is terminated when the indentation stops. And the indentation is dependent on like how much indentation you started with. Mm-hmm. So you have to like, if you think about implementing that function, you have to like determine how much indentation you have and then like kind of work your way around here. Or you have to do what Python does, which is like hack your way into like a preprocessor on the tokenizer, which is really dumb. We don't want to do that, right? Like, so here's the thing, right? I am like very anti-hack in the field of parsers. I hate hacks. But like almost every major parser and like all these major parser algorithms, they force you to implement hacks. They force you to contort your grammar so that it's not like formally beautiful anymore. It's like this contorted weird thing. They force you to like inject things into your tokenizer, like Python and Haskell do. Like none of these are great solutions. I like nice, clean solutions. So my goal as a parser theorist is to push towards clean, formal, precise, tractable, reasonable solutions that also run really fast. I like to live in utopia. And you'll notice right away that we're already in contorted formalism land. Because on the previous slide, we have this thing that's like, you know, an expression followed by a plus followed by an expression, right? Like this makes sense. You just have any number of expressions sort of chained together. This is formally describing the grammar of, addition and subtraction. That makes total sense. But this, we've like had to split things up a little bit. Now we've got this term thing. And like, for some reason we had to put T on the left and E on the right. That doesn't make any sense. If it looks ugly to you, it's because it is. This is ugly, right? This is no matter what you learn in compilers, this is not meant to be understandable. What we had to do here is we had to contort this so that the machine could understand it better. The machine in this case is our algorithm, and the algorithm is recursive descent, and it looks like this. So we're going to write a recognizer rather than a parser. And the difference between the two is that a recognizer returns Boolean true false. It just says, yes, this is valid. No, it's not valid. Believe it or not, these are actually very useful. Like AT&T runs these things at scale. But normally you're writing a parser that returns like an AST or a value or something like that. You can extend this algorithm pretty easily.
Daniel?
Yes?
I think that the return type must be declared.
Yeah, lots of return types have to be declared. I told you I didn't compile it. Compile with your mind. Pretend that Scala has better type inference than it actually has. All of these functions return this type right here. So pair of Boolean and list of characters. So what I'm returning from every function is Boolean true false, yes or no, and the continuation of my parse stream. So how much more of the parser, so how much more of the characters I need to go through. Those of you who are sharp-eyed in the audience, are immediately realizing that I could have done this with option. And that is absolutely correct. And I'm only realizing it just now. So yes, this is isomorphic to option of list of car, right? Like they actually convey the same information and would have been more composable and would have made the code cleaner. We're going to deal with dirty code. So all right, so how do we recognize a character of streams, right? So return true if these streams are a valid set of integer expressions. Like for example, here's a valid expression, right? 1 plus 2 or 1 times 1 divided by 1 times 1. That's apparently valid. At least according to this grammar. Oh yeah, and we could we could just throw parentheses around it. So this is valid, okay? What we're trying to do is we're trying to recognize this, and also things like this, which regular expressions categorically cannot do, but also reject things like this, which is invalid. Okay, that's what we're trying to do right now. All right, so we start off, we say parse E. All right, well that makes sense. E is the first thing in here. Parse E. Well, how do we have to parse E? Well, the first thing we have to do is parse T. Right? T is the first thing we have to parse if we want to parse an E. So we parse T. Parse T is down here. Parse T, we look to see, oh, did we get a parentheses? Maybe we got a parentheses. If we did, parse an E, and then go and see if we get a closing parentheses, close it off. If we got a 1, then we're so far so good. Just return our results and keep moving along the chain. Back to parse E, if we successfully parse to T, well, maybe we're done, or maybe we have some other stuff to do here. So parse E tail, well, if we're done, right, so if this is the end of the stream, then just return true, right? So an individual term is a valid expression. Or if we see times or division, well, we're just gonna parse E on the tail, and if that tail is valid, right, this part right here, then we're good. Very, very simple and straightforward. And you could have encoded this even simpler than I did. I just forgot about option. Basically the value of this, and the reason it's so great and such a good place to start, is recursive descent encodes the sort of the shape of the grammar in the code that you're writing. So whenever you have a recursive rule in your grammar, like the one that I'm highlighting right now, that is a recursive call. Like we're recursively calling to parse E, right? So this is kind of cool. Right? But there's a lot of problems here. So there's no problem if this is a recognizer, but if we were doing a parser and we were producing an AST of this division and times thing, and an AST is a structure, right? We're building a tree of all of our expressions. If we were doing that here, does anybody see what the problem is with what we've written? What would be wrong about the AST from what we logically think about of math?
It's on the right.
It's on the right.
It's completely on the right.
It's all completely on the right. Yeah, our AST would be completely right-leaning because the recursive, right-leaning from your perspective, because the recursive call to parse E is on the right. It's on the right-hand side of times. So that's kind of unfortunate because we generally think of times as associating to the left. But here our grammar is going to construct a tree that associates to the right. And you do not want to know what I would have to do to this to make it parse with the correct associativity in recursive descent. I would literally have to refactor this grammar into 8 rules. That is awful. Why are we refactoring our formalisms to contort to our algorithm? That's just a bad algorithm. Now, to be clear as to why we had to refactor this, imagine if up here, instead of T, imagine we had E, all right? Well, what would we have done? We'd have gone into parse E, and we're the very first thing we have to do is parse E. And now we're infinitely recursive and we never make any progress. So this algorithm, this mechanical transformation from grammar to parser, is insufficient. It doesn't support something called left recursion. Now, there's something really, especially the mathematicians in the audience should be kind of cringing a second here, because left recursion implies that somehow this is different than right recursion. There's apparently something weird about left recursion versus right recursion, and this is actually one of the really interesting things about parsing, is that things that are on the left really are different, algorithmically. You have to treat them differently, you have to think about them differently than things that are on the right. And the reason for this is we walk through the input stream, starting here, in a left to right fashion. That's actually kind of weird if you think about it. Why don't we just go right to left? Or why don't we start in the middle and fractally loop our way outwards? No one knows. That is so my research right now is like thinking about that. Like what would happen if we could just like start in the middle and like sort of recursively deconstruct our stream? Like could we come up with a better algorithm? That is a topic for another exciting day. Or like the hallway after the talk. So there are other algorithms that we can use to try to solve this problem of left recursion. Now, how many people here took a compiler's course somewhere? A lot of people, holy crap. Wow, this is like the right room. All right, how many of you like use Bison or Yak or something like it? Yeah, anybody have fond memories? A couple people? Wow. Wow. See me after class. Like Bison is kind of cool, but it's like super arcane. And the problem is that Bison implements an algorithm called LALR1. That is, I said that really fast, so I'm going to write it down. LALR1, as distinct from LALR2. So LALR1 means look ahead, left, right, 1. That probably doesn't help you at all, but if you have trouble remembering the acronym, that's what it is. Basically, LALR1 is an algorithm that people describe it as bottom-up parsing. I hate that metaphor, it doesn't make any sense. But basically what it's doing is it's looking at the grammar kind of as a whole. Rather than starting from the top in the case of like E and being like, well, I'm going to like, you know, literally imperatively work my way through the grammar. And it says, well, what state could I be in now? All right? Well, now let's say I saw this token. What state could I be in after that? And there's an algorithm that's actually really beautiful. You can express it as a regular expression, but there's an algorithm for you know, sort of taking context-free grammar and deriving this set of states and figuring out all the states that you could possibly be in at any given point in the parse and then linking them up. So that's kind of cool. And in practice, it looks like this. Now, you guys are going to get a treat, because I literally hand-coded this in the back of the room while trying to understand category theory. And this is like probably completely wrong. But what I'm doing here, so this is different than Bison's implementation of an LALR1 parser. Bison will do things like it'll encode its state machine as literally an array of arrays. And it'll index into that array of arrays, like based on token and state number, and like figure out, oh, next state is over here. And so that's super fast, at least in C, but it's also like unbelievably ugly and impossible to understand the code it generated. The technique I used to generate this here, and again, I literally did this by hand, so please do not put this code into production. But like the technique I used here is called recursive ascent descent. There's some papers about this, but basically it's a way of encoding LALR without using tables. Like instead of using an array of states, you actually just write functions just like we did with recursive descent. And now the algorithm for recursive, or the argument for recursive ascent descent as an algorithm is like, oh, well now people can write LALR parsers by hand. No, you can't. This is like really hard. Like I've written recursive ascent descent parsers by hand before, so I've got like probably about as much experience with this as anyone in the world. And this was like, I probably completely got it wrong. And this is a super trivial grammar. No one's writing a compiler like by hand that uses recursive ascent descent, aside from James Godwin. Yeah, actually true story. Java's parser uses this algorithm for reasons that Gosling alone knows. So here's what we're going to do. We're going to represent things as states, which means that we no longer have nice function names like parse E or parse T or anything like that. We actually have to like have an opaque state machine, as one does. And what we're going to do is, as a documentation thing, and because it was completely impossible for me to do this otherwise, in front of every function, state function, we're going to write where we could possibly be in the grammar. So this notation, this dot, means that we are right here in the input stream. Okay? We're right here in the parser grammar. And so, for example, if I was to consume a 1, that would mean that all of these like branches would die out, and I would be right here. Okay? So that's what the dot notation means. This is how you can kind of follow how you're going through this. And this notation is consistent with what Yak and Bison and basically everybody use. So the first thing we're going to do is we're going to look to see, well, I mean, we have to see what are our set of terminals that we could possibly see. A terminal is anything that's in a quote, right? So it's a non-terminal is something that's not in a quote. I don't know exactly where that notation came from, but so our set of terminals, so we've got an open paren. If we get an open paren, go to state 2. And then if we receive some results from state 2, we're going to end up over here, so we'll have to like cheat and move forward. If we see a 1, go to state 5. And if that works successfully, we're going to go to state 6. But we like some of this is like back and forth here. Like I actually had to write, like I wrote half this code and then I wrote the rest of it and then I came back and wrote the other half. So this can kind of like tell you how much of a mind like bend this is. All right, state 1 is just like, oh, we're over here. We're like parsing a term. Nothing particularly exciting. We're at the beginning of the term. Look for stuff. Move to state 2, move to state 5. All right, state 2, we're halfway through this. Nothing particularly exciting. Parse E is probably not the right name. I'm guessing this is supposed to be state 0. I hope. Yeah, so anyway, so moving along in the way, et cetera, et cetera. Okay, we got to the end of a thing. Now this is what is generally called a reduction or a reduce. All along we've been shifting, right? You're sort of taking the dot and you're shifting it over something that you have successfully parsed, all right? So when we get to the end of the line though, we have to do a reduce. Now, if this comment on line 72, if we were in a state where like simultaneously we had like, you know, some other thing over here, let's call it like F, and this F was like, you know, like this or something like that. Yeah, let's do that, and then this, and then maybe something came after this or something horrible, like 42, right? So let's imagine that this was our state. This would be a conflict, all right? So in LALR, if you've ever used Bison or Yak, there's always the dreaded shift-reduce conflict that no one knows how to understand, and you just like poke at your grammar until it goes away. This is a shift-reduce conflict, okay? Now obviously, like I just like synthesized this state out of thin air, but we could put it in the grammar and I would show you. In a shift-reduce conflict, we're trying to reduce because we got to the end of a line, but we also sort of have this other thing over here that maybe we would need to parse. And the algorithm has to make a decision, the state machine has to make a decision, well, which one am I going to do? Am I going to shift? Or am I going to try to shift rather? Maybe the next token is at a 42. Or am I going to try to reduce? And it doesn't know which one the right one is. So LALR just borks on this. A really easy way to get shift-reduce conflicts is to do like our arithmetic grammar, like E plus E thing, and then literally write the expression like 1 plus 2 plus 3. That will generate, well, I mean, the compiler will find this ahead of time, but this is what it's talking about, where it's like, it's at this point, and it doesn't know whether it's supposed to reduce the 2, and the 1 plus 2 to create an expression, or if it's supposed to wait and reduce an expression on the right-hand side. So shift reduce is one of the ways that like an ambiguity can show up. It's because, well, we don't know what associativity you're trying to declare here. So shift reduce is a problem. Reduce is also a problem, but much more rare. But basically LALR just can't handle situations where you get to the end of the line and there's more than one option. Aside from really special circumstances that no one understands. All right, so we reduce, life is good. All right, here's another state, we reduced on that one. Here's a state where we're handling some left recursion. Now, I glossed over this at the top, but remember that our grammar looks something like this. We're no longer hiding the E on the right, we're putting the E on the left now. We're taking advantage of left recursion, but I still have this T thing, right? So I still had to use this term thing just so I could avoid a shift-reduce conflict, okay? So again, we're contorting our grammar, we're contorting our nice formalism to meet the demands of our algorithm. So we're already in territory we don't want to be in. But pedagogically, it's still interesting. So down here, I just want to show you quickly how left recursion is handled, and we're not going to spend like a million years on this. But basically what's going to happen is we're in this state right here, where we just finished parsing a term. This is a look-ahead state, by the way. We just finished parsing a term. So we could be at the end of an expression, and we could also be like just about to consume a times and a div and like moving on with another expression. So this can be encoded without look ahead, but I'm lazy, so I encoded it with look ahead. And basically what we're going to do is we're going to say, well, look at the stream, but don't consume it. Okay? So this is just a little pattern match deconstruction. Look at the stream and don't consume it. Is the next character times or div? Because if the next character is times or div, then we must be in one of these two states. If we're at the end of the stream though, then clearly we're in this state and we're done. Actually, now that I think about it, this is just going to completely do the wrong thing. Yeah, don't run this code. You get the idea though. All right, so this algorithm is very opaque. It's very crazy. If you want to see an example of recursive ascent descent, like literally a parser that's a lot like this, but slightly less trivial, that does real things, there is an example on Wikipedia written in Scala that I have actually compiled and run. So you can go look at that as long as the editors haven't deleted it yet. That is basically interesting but not interesting. Okay, so we have so far seen two algorithms. We've seen recursive descent, which implements a form of unrestricted
I'm sorry, what the one stands for in the algorithm?
Sorry, what?
Look ahead, left, right, one. What's the one for?
Great question. So how many characters are we looking ahead in this look ahead state? Okay. Exactly. So LALR1 looks ahead only one token. Prior to some formal work, people talked about things like LALR2 and LALRK, which was like a configurable look ahead. But then someone went and proved that all of the grammars that are LALRK are actually also LALR1, so that nobody cared anymore. Like, you just need to be a little careful with how you generate states. And like I said, like, look ahead allows you to be a little bit lazy sometimes in like how you generate states. This is a good example. Like, I don't actually need this look ahead state. If I had thought more carefully about what I was doing, I could have done it without look ahead. But look ahead just gave me the option. TJ.
Is there a reasonable way to count how many states you'll need looking at a graph?
Is there a reasonable way to count how many states you'll need? Yes. Define reasonable.
Human doable on a piece of paper within
Within a time proportional to the age of the human. No, there is not. So the algorithm for computing the states is regular, which means that if you wanted to, you could encode it as a regular expression. So in other words, a Perl one-liner. But like a Perl one-liner, you don't want to evaluate it in your head. And I've done exercises like that where, like, for non-trivial grammars, I've like computed the parse states by hand, and it's like a mess. And hilariously, when I did it, like, the solution to the homework was wrong. So like, even the professor had gotten it wrong. It was just really bad. It's very, very, very fiddly stuff. Very fiddly stuff. I don't recommend this algorithm. Other than that, it gives you left recursion. Like, that's basically the advantage it has. It gives you left recursion, which is cool for math. But we're still in a state where we've contorted our grammar, okay? And that's because, thus far, we've been working in a restricted subset of context-free languages. So here's something that I want to point out to you. This grammar has an ambiguity, right? It actually has multiple ambiguities. And you can see the ambiguity in 1 plus 2 plus 3, right? Does this mean 1 plus 2 plus 3, or does it mean 1 plus 2 plus 3? Like, which of those is the right answer? The grammar doesn't say. So this is ambiguous. But neither of the algorithms we've been writing so far are able to handle this sort of scenario. In one case, you'll get, like, I don't know, some sort of stack overflow, I guess, if you do this in recursive descent. I don't know. In another case, you'll just, like, you'll get a shift-reduce conflict or a reduce-reduce conflict. So clearly, this is a valid grammar. Formally, it is a valid grammar. There's nothing wrong with this grammar. The problem is with our algorithms. Our algorithms can only handle the unambiguous subset of context-free languages. Now, I want to pause on that for a second, because there's some distinctions we need to draw here. There are context-free languages which are inherently ambiguous, all right? So where you've written it in such a way that, that is a thing, but it's not a thing I want to talk about. There are context-free languages which are globally ambiguous, which is where you generate this grammar that you go all the way to the end of the parse stream, and when you get to the end of the parse stream, you have two answers. Like, that's a globally ambiguous grammar. And there are grammars which are locally ambiguous. So in a locally ambiguous grammar, this is a little bit harder to see, but in a locally ambiguous grammar, you start from the beginning of the parse stream, and you're going on and you're going on, and then all of a sudden you get to this rule where you're like, well, I don't know what the answer is. So like, oh, I've got two answers here for a while, and then somewhere along before the end, you can prune one of them off. And you have one answer at the end of the day. There are actually a lot of locally ambiguous grammars that are not globally ambiguous. This is a really, really important point. Parser theorists of a particular school of thought that I will not speak of are of the will tell you that ambiguity is bad. Ambiguity is really bad. You can get this ambiguous result at the end, like you don't know what to do with it, and your algorithms are slow, and dear God, it's terrible. I would submit that ambiguity is good. Because what ambiguity allows you to do is it allows you to embrace the full formalism. So when you can embrace the full formalism, you get the full properties of context-free grammars. Context-free grammars, for example, they compose. If you have two context-free grammars, you can glue them together, either with the OR operator or just like sequentially, and the result is a context-free grammar. But if you have two unambiguous context-free grammars, and you compose them together in the same way, the result is not guaranteed to be unambiguous. This is a really, really, really important point. Context-free grammars are closed under composition. Unambiguous context-free grammars are not. And so this means that these tools that we generally work with, like recursive descent, like LALR, even parser combinators, they are giving us, they're not giving us properties that would be really, really, really nice to have. Properties that as functional programmers, we begin to expect and sort of demand from the universe, because it's just so much easier to think about things when closure holds. So rather than contorting our formalism, what if we could just contort our algorithm? What if we could come up with an algorithm which is smart enough to handle ambiguous grammars and figure out all the mishmash of stuff and come up with results at the end of the day? And the answer is, we can. There are a lot of these, and I will not be talking about almost all of them. If you are interested in like some very light reading, I recommend looking at, in order, early parsing, that's EARLEY, and GSS, Graph Structured Stack. That's a paper in 1995 by Tomita. It basically, the graph structured stack set the stage for about a decade and a half of parser research. And graph structured stack is basically, it's really, really simple. So when you do like recursive descent, you have a stack that you're working with, right? And you can pop back up the stack. Well, what if your stack could fork? That's a graph structured stack. Now, well, more specifically, that's a tree structured stack. So Tomita's great insight was like, when you fork your graph, because you're working within the constraints of the context-free grammar formalism, you could prove that in all cases, you're eventually going to prune back. So he calls this shared suffix elimination, but basically your stack forks, but at some point it actually does come back together again. And because it comes back together, you know that you can bound the sort of potential counting space of your states, right? So rather than just having like an exponential space of functions that you're calling, like recursively descending down, you actually prune it down, and it turns out that all GSS algorithms are at least cubic. So that's cool. And there's a lot of GSS algorithms, and they're really confusing to understand. I've implemented a few of them. They're really cool. I recommend looking at GLL if you're looking at one that's can be implemented by a human being. The other ones cannot be implemented by a human being. Really they cannot. We are not going to talk about any of them because we don't have to anymore. So I think 5 years ago now, a researcher, then an untenured professor at University of Utah named Matthew Might, was working on something with one of his students, David Darius, based on an old bit of research called derivatives of regular expressions. And this bit of research is like from the 1970s, right? And it's basically this thought, and I'm just going to like show you a quick regular expression, right? So let's say we have like, you can have a D or a number followed by anything followed by like either an A or a B. Okay? This is a regular expression. And let's give some quick input, right? So we can have like a 1 followed by a percent sign followed by a B. This is valid in this language, right? So the notion of derivative regular expressions is that you can take this style of thing, this input, and parse it with this regular expression by successively deriving new regular expressions as if the first token had already been consumed. So here's how that works. Here, we'll go start down here, All right, so we're going to do one derivation. We're going to derive with respect to 1, right? That's the first character in our input stream. So what we're going to do is we're going to get a new regular expression which looks like this, and a new input which looks like this. We just lopped off the first character and then lopped off the first thing in the regular expression that matched it. Now we can do this again and derive with respect to %. Now we lop off again, and now we're down to B and AB. And we finally do like an overwrite of our buffer because we don't know how to type. And we derive with respect to B and get nothing, which means that we won. Nothing is good. And if you squint at this long enough, you'll realize that you can apply this to any regular expression. And this is actually a really easy algorithm to implement. So if you want to like waste a little time on the flight home, implement this algorithm for regular expressions. Like you can literally write a regular expression engine in like 5 functional lines. It's very, 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 very simple. Matt Might now has his undergrad students do it in like week 3. So like it's a really fun exercise. So anyway, what Matt Might's realization is that you could take this concept and apply it to context-free grammars. Because a context-free grammar is really nothing other than a recursive regular expression. So if you take this, yes?
Just a question. Is this algorithm the one that Google has implemented?
Is this algorithm one
regular
that...
expression without doing the creating the
Is this the one that Google has implemented? I don't know. It's possible. There's some reasons not to use this algorithm. Most notably, it's slow. Like for doing regular expressions, there are just more efficient algorithms for this. Because like if you think about it, what most regular expression engines do is they compile, like they literally compile in memory to a
yes,
DFA.
that's what the Google implementation doesn't do.
Yeah.
It doesn't compile the regex.
So they could be using derivatives. There's a couple of other techniques for doing this with regular expressions. Derivatives just happen to be the one that Matt Might was looking at the time. So I don't actually know enough about the Google research to tell you. So grammars are recursive regular expressions, which means that if we can find a way to derive over recursion, we could implement parsing for arbitrary context-free grammars using nothing but successive derivation. And it turns out that the answer to this is literally functional languages. So most functional programming languages have a construct called laziness, where you just defer evaluation. And if you can define that, like this allows you to sort of back off and say, well, if I can define what it means structurally to derive over recursion, I don't actually have to look at that result. I don't have to do like the infinite recursion depth thing that you can see where this is leading to. I can just produce a result that's like, I defined what it means, and then later on it will eventually be forced. Now that sounds like magic and witchcraft, but it turns out that in this case, the magic and witchcraft summoned the frog. So this is a really, really incredible algorithm. And literally, like, in many ways, I think this is easier to implement than recursive descent. It really is. So this is a real implementation of it that I have compiled and has tests. But that also means that it's a little bit uglier and like folds off the screen a little bit. There's a lot of stuff on screen right now which you should not care about. So there's things like def tilde and like tilde arrow and like whatever the heck this operator is, and like, oh, I guess we're writing Scala because soup. But the interesting thing is map, okay? Everyone knows what a functor is, so like we can hold on to map, okay? And map produces this thing like parser.reduce, okay? Well, that clearly implies that parser, like if you're familiar with free functors, parser has to be some sort of free functor, and like there has to be something in the grammar. So like all good functional programmers, let's see what the let's see what the algebra looks like for parser, all right? So parser has a couple of cases here. You're gonna have to take my word for it because it wraps off the screen, but all of these classes extend parser, all right? So the first case in our algebra is sequence. And sequence contains within it a left parser and a right parser. And it is a parser. So sequence, we're composing two parsers together sequentially to get a single parser. The second case in our algebra is the really complicated and scary one. And this is literally as scary as it gets, I promise. It's union. So this is the pipe operator. So remember I said there were two ways to compose context-free grammars to get a context-free grammar. One was sequentially, one after the other. The other one is via alternates, either this or that, and you're closed under both. So clearly any true parsing algorithm, anything that can actually handle context-free grammars, must have this underneath there somewhere. Some way of saying, well, if I start with 2 grammars, I can get 1 grammar either by alternation or by sequence. So union is a parser. It says it has a left parser and a right parser, and it returns a parser. This encoding here is actually function to parser, and this is function to parser. And the reason I have to do this is because Scala is an eager language, so I have to be really, really careful that when I compose things via union, I evaluate that lazily, right? This is really fundamentally important, because if it weren't for that, then anytime I constructed a parser that was like left recursive, it would just be, or recursive in any way at all, it would just be infinitely recursive right away, and it would never be able to construct the structure, okay? So, and then we like, here's our call by need stuff. So we have a left and a right, and it's done. That's not interesting. Reduce. So we're actually doing a parser this time. We're not doing a recognizer, because recognizers are not, like, you can do recognizers via parsers. And reduce says, I'm taking a parser and a function that looks a lot like map but has this extra stuff in it for pragmatic reasons, and returns a parser of B. Okay? So this is literally like, this is sort of like our free functor case, right? Where we're saying we can map over parsers, a parser of A with a function from A to B, and get a parser of B. Pretty straightforward stuff. Literal. Now we're starting to get into things that are sort of the bare bones, right? So I said these were called terminals, right? They have quotes around them. This says literally parse the string literally. And that will give us a parser that produces a string. If you've ever written a parser combinator framework, some of this stuff is going to start looking really, really, really familiar, because we've all written this stuff when we've done that in functional languages. And finally, we have this final case called epsilon for historical reasons that just says, I accept the empty string. The empty string is epsilon. Don't ask me why. And if I accept the empty string, produce the value of type A. There's also a failure case, which is analogous to this. So in a real parsing framework, you actually really need to keep track of errors, because you need to present them to users at some point. And a lot of parsing algorithms actually forget about this fact. All right, so how does the actual meat of it go? And I'm going to finish up real quickly so that John doesn't have to drag me off the stage kicking and screaming. All right? So let's look at apply. Apply is a function, we're on parser now, so apply is a function on parser that takes a line stream. Now, you don't have to worry too much about what line stream is, but you can think of it like a stream of characters, okay? There's more to it than that. This is actually a stream T of string, but it's a string it's characters, right? It's just characters. And what we're going to do is we're going to look at this line stream and pull out and derive with respect to the first line that we see. And what the derive function will do is it will take the first character of this line, providing that the line is non-empty, and derive, we're already making sure that it's non-empty, like we normalized things. That's what this does, is it like gets rid of empty lines. So we make sure that we don't have an empty line, because that's dumb. And we pull out the first character of the line, and we derive the current parser with respect to that character. Just like we were doing with the regular expressions, where we're like, well, take the first character, take the first token of the regular expression, match them up and throw them away, right? That's what we're going to do here. So let's look at derive really quickly. Derive does some super scary stuff with vars in Scala. Boo hiss. And the reason it does this is because Scala's laziness doesn't allow non-local memoization. Basically, we have to memoize the function very carefully. And the Haskell implementation has to do something similar to this, just not with vars. And it turns out that the easiest way to do this is to have some vars on our thing. But don't worry about the implementation logic so much. Worry about the fact that what we're doing is we are memoizing the fact that we derived this parser with respect to this line, and we got this result. Okay? That's all it is. It's just laziness. It's really just laziness. It's just because it's a function, we have to have a memo table. So what we're going to do then is, this is literally just memoization logic. The actual logic of derivation is implemented by this underscore derive function. So underscore derive. Let's look at how it's implemented for literal. All right? Literal should be really simple, right? We literally have the string in our hands. There's no complex logic. So what do? Well, we literally say, first character of the string that I'm at right now versus the first character in the line. Are they the same? Yes. If they're the same and we've completely consumed the literal, then we're done. And we can return epsilon, which is, we're set with the empty string. If not, then we have to increment our offset along, which basically says, I'm a parser that consumes this literal, but I'm sort of partially through it. Otherwise, if it doesn't match, then we've gotten ourselves into an error state, and we just immediately produce a failure. So now remember, there might be other branches of the grammar that are successfully consuming this token, but we don't care. Like, this is a really dumb algorithm, right? It's just like narrow in on the case you're on. The case we're on is literal. The literal we have is the one in our hand. They don't match, so we have a failure now. Done. Really straightforward. Epsilon. Well, what does epsilon look like? Well, if you try to derive it, it can only consume the empty string, and all of our lines, remember, are non-empty. So the only derivation for epsilon is failure. And failure, somewhat intuitively enough, the only derivation for failure is also like failure, right? The same failure. So most of the time we're failing here. We're not really succeeding very much. What about the other cases, right? Reduce is pretty trivial, okay? So reduce, by the way, ignore the render functions and like all of this stuff. I collapsed it on purpose. It's literally just rendering the graph. That is more complicated than parsing. Like, it's just pretty printing, and the pretty printing logic is bigger than the parser. So deriving a reduce is simply deriving the parser inside the reduce and then building a new reduce around it, right? It's the free functor. Like this is what counata looks like. So if you ever take a look at that. What about union and sequence, right? These are the two recursive cases of our ADT. Like what is this actually going to look like? Well, naturally enough, things are a little bit more complicated. So let's start with union. Union, the derivation of two parsers composed with the pipe operator is the derivation of the left, pipe, the derivation of the right. That seemed complicated. So what this is literally saying is that whenever you have a choice in your grammar, you have two grammars that are composed via alternation, then the derivation of that whole thing is, well, derive the insides, and it's one of those two. That's actually really intuitive when you think about it. And it turns out that because this pipe operator, I've defined it very carefully to be lazy, this is what saves us. And the whole algorithm sort of hinges on this little trick right here. But this line, you can define this in any serious functional programming language. This is not difficult to write. We haven't done anything crazy yet. So let's go to sequence. This is the last thing to define. Let's see if we do something crazy in here. Well, here's the definition of derived for sequence. This looks a lot crazier. So let's pick it apart. Line, all right, so we're deriving with respect to line. Well, the first thing we do is we look at left, and we say, is left nullable? That's kind of an interesting question. Is it nullable? Well, clearly this doesn't mean Java null, because God forbid. So what does it actually mean? Well, nullability actually is nullable is one of the three fundamental functions that you need to implement to do derivative parsing. So you need to implement derive, you need to implement is nullable, and you need to implement something called finish. So is nullable simply says, is there a case in this grammar that I represent that would consume the empty string and return a value? In other words, can I find an epsilon? That's all it's asking. So the is nullable function is supposed to kind of look through the parser and figure out whether or not it's nullable. And we can memorize the result of this too, and in fact we need to. So the definition of is nullable, really, really quickly, is like this thing that looks very scary that is implementing a least fixed point operation. But if you think about it from sort of like peel it apart from like a graph traversal standpoint, because remember our parsers are recursive, all we're doing is we're keeping track of the parsers that we've seen. And if we see a parser a second time, we just say, oh, we don't know what the answer is. TJ.
Is nullable similar to a recognizer?
Yes. If we were just writing a recognizer, is nullable would be the final answer. Like, if once we get to is nullable true, or well, if we consume the entire stream and then is nullable is true, we don't care about anything else. But for a parser, we have to carry the results along with us. Either way, we still need the function. So this is just like traversing the graph. Like if we see a parser that we've already seen as we've sort of gone down the graph, that just means we don't know the answer yet, and we'll figure it out later. But in every other parser, if we see an epsilon, well, that's nullable. If we see a literal, that is not nullable. If we see a sequence, well, or sorry, if we see a union, well, it's nullable if the left or the right is nullable. We're just sort of following the structure of things. So let's go back to our derive here. So we were in sequence. And we were looking at nullability. So if it's nullable, in other words, if the left-hand side of this sequence can consume empty, then we need to consider two separate cases now, right? One is where the left side was empty, and we're now in the right side of the sequence. The other case is where the left side wasn't empty, so maybe the left side is nullable, but it could also consume other things if we gave it to them. So we have to consider either left side is empty and we're already in the right, or left side is not empty and we still have to sequentialize with the right. So all of that means, and this stuff right here, like this is just keeping track of results. What this boils down to is simply left.derive line, tilde right, or right.derive line. That's what's being implemented here. It's ugly because we have to keep track of results. But this line, this is what we're actually doing. Okay? Now tilde is sequential composition. So the second part here is literally what I just wrote. Left.derive of line. So if the left-hand side cannot consume the empty string, that means that any derivation we do as a sequential node has to start with the left. We have to derive on the left. So we derive the left and we re-sequentialize with the right and we're done. This is the whole algorithm. This code runs. I have tests for it. It compiles even. So like, this is it. Like all of the ugliness you see on here is basically just Scala, right? Like this is not a complicated algorithm. And here's the crazy thing. This is fast. This is really fast. The constant factors on this algorithm are competitive with LALR. So think about how fast Bison runs. If you implemented derivative parsing in C, it would be almost as fast. So those are the constant factors. What about the asymptotes? Remember that we're consuming this ambiguous grammar, and people could give us a grammar that's really terrible. Like here's a valid grammar, right? Like, dear God, who in their right mind would write this? But like this is valid. This is a grammar. We have to produce a parser for it. We have to accept it. So if we run this grammar on like a string of A's, that dear God, why is like Apple being stupid? All right. So if we run this on a string of A's, what is the runtime of this parser as proportional to the length of this string?
Over 9,000.
It's not over 9,000. That's the amazing thing. This parsing algorithm is O of n cubed. How is that possible? It's like it actually comes down to like a really complicated counting algorithm, a counting problem, and there's a paper that came out quite recently that kind of goes into it in more detail. I can show you the paper if you want. It's super readable. Like this paper is like really, it's one of the few that's really well written. Like very, very easy to read, very easy to consume, but formally grounded and a ton of benchmarks in it. So it's like perfect in every detail. This paper shows that it's O of n cubed. So this is literally the holy grail. We have a parser that you can implement that is easier to implement in a functional language than an imperative language. You can implement it in realistically like 15 lines of Haskell. It is fast from a constant standpoint, and it's fast from an asymptotic standpoint, like literally as good as the state of the art. Why would you use anything else? This is it. So I'm like really, really excited about this algorithm. And this is why I'm building a framework for it in Scala. But John is about to pull me off the stage. Does anyone have any more questions? Like questions about stuff, challenges, things?
Why are we not using this algorithm?
That's a good question. Well, people haven't written enough tooling yet. Until the most recent paper came out, people thought that it was exponential. Mostly because I thought it was exponential and like nobody corrected me. So like this is literally my fault. Like for 5 years this algorithm has been stagnant because I made an informal argument that was wrong. So the paper corrects me and it's great now. Like it actually is n cubed. Yes?
So when you are deriving the regular expression, what do you do for like, this could be anything and there could be any number of them? And then, oh, by the way, it ends with either A or B. Like, how do you decide that?
Right. So like it's so like a star combinator or a plus. Yeah. So you do it just the same way that you do it in the parsing algorithm, right? When we're doing it with context-free grammars, you represent the star or the plus as not a star or a plus, but rather like sequentialization or like thing, right? So you basically generate an OR, right? Remember when we derived the sequential operation? We generated an OR that was like, well, maybe we're in this case where the left was nullable and we're consuming the random AB at the end. Or we're in this case where we're still recursing and we have to like consume more like C stars, right?
Right.
So you generate an OR in the middle, and you keep going along. This is the thing that's a little bit counterintuitive about derivative parsing, is that it doesn't shrink the grammar. In fact, derivative parsing actually grows the grammar. Because anytime you derive a sequence operation and the left side is nullable, you will get another node in your grammar, the OR node, right? Everything else just stays the same. So the same thing is true with deriving regular expressions.
Okay.
Yeah, I really do highly recommend implementing like derivative regular expressions. Just like follow your nose and do it intuitively. I promise you, you'll like the results. Like it's very straightforward. Follow it along. Any other questions? Okay. Oh yes.
Yeah, but thinking about how deriving with the functional language, does this make forget the tokenization or go directly to embedding the logic in the parser or something?
That is a great question with a very long answer. So the short answer is when you use a general parsing algorithm like derivative parsing or GLL, you can embed your regular expressions directly in the grammar, and it still works. If you use a deterministic parsing, an unambiguous parsing algorithm, like LL or LALR, you can't put the regular expressions in the grammar. You have to have a separate tokenizer. The only exception to this are peg parsers, because peg parsers don't parse grammars. But see me afterwards, I will give you the long form answer, because it's fascinating. There's a lot of interesting research on that. There was another question in the corner really quickly, and then John is steaming up.
Yeah, quick one. Why not Haskell?
Why not Haskell? You know what? I just like pain. And the JVM is just JVM-like. And there isn't a longer answer.
Well, if it's 15 lines of code, you can do it for tomorrow.
Yeah, I probably could, except I don't know Haskell well. But yeah. Like Gabriel could do it for tomorrow if he wanted to. Like, no pressure. But like, like it's really there's a reference implementation in the original paper that is literally 15 lines of Haskell. Making it a parser rather than a recognizer is tricky. Like all of that ugly code in there, aside from the stuff that was rendering graphs, is just like keeping results around. If you don't have to keep results around, like you're literally just trying to answer Boolean true false, it's so trivial. Very, very, very trivial algorithm. Doing it in Scala, like I work in Scala, a lot of people work in Scala, we need a framework in Scala. Someone else can write the one in Haskell. Thank you.